Let us now write down the coefficients contributing this matrix. Let us write down the labels T, R, V, okay. L, N, P, H, S, W, then M, O, Q. There is an order of writing this. Actually, if you look at them carefully, T or V are actually translations and L and P are rotations at jth end. So, let us carefully write it here. These are x, y, z translations at jth end. These are x, y, z rotations at jth end. Naturally, this will be H, S and W, then M, O and Q, okay, will be x, y, z translations at kth end. This is x, y, z rotations at kth end, correct. Let us also mark the labels here. This is T, R, V, then L, N, P, H, S, W, M, O and Q. Okay. So, now these are happening at the jth end, these are happening at the kth end, and these are forces and these are moments. Similarly, these are forces, these are moments. Okay. Let us fill up these values. When you give unit displacement along T, only T and H are influenced, you see here, only T and H are influenced. Okay. So, KTT, then KHT, remaining all are zeros. Similarly, when I do it for H at the kth end, you see it will be KTH and KHH, remaining all will be zeros. Okay. When you give unit displacement along R is along Y. So, you get moment about. So, you are doing on xy plane. So, R, P, S and Q are invoked. Okay. So, let us do that. When you give along R, P, S and Q are invoked, remaining all are 0. Similarly, at the other end, when you give along S, you know R, S, P and Q are invoked, remaining all are 0. When you give unit displacement along V, let us see here along V, V, N, O and W are invoked. So, when you give along V, V, N, so K, V, 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 N, O and W. Are invoked, remaining all are 0. Similarly, contemporary at kth end will be W. So, K V W, K N W, K W W and K O W. Okay. Remaining all are 0. So, 0 0, one more 0, 1 3 zeros, W W, zeros, 1 0. Okay. Now, let us give moments about L. When I give moment about L, L and M are invoked. So, L and M are invoked. So, L and M are invoked, remaining all are 0. Okay. Similarly, at M, L and M are invoked, remaining all are 0. So, 3 zeros and 2 zeros. Now, we will give unit rotation about N, V N, O and W are invoked. Okay. So, V N, O and W, V N, O and W are invoked, remaining all are 0. Similarly, contemporary O will be K V O, K N O, K W O and K O O. The last one is rotation about P. So, P Q R S will be involved. So, K R P, K P P, S, K S P and K Q P, remaining all are 0. Similarly, Q, so K R Q, K P Q, K S Q and K Q Q, remaining all are 0. So on. Okay. So, friends, I do not think you have any difficulty in entering this matrix for a 12 by 12 for a member, identifying the corresponding degrees of freedom influenced by giving unit displacement along x y z and unit rotation about x y z both at the jth end and kth end respectively. Now, our job is to fill up these values of coefficients from the known principal quantities of beam element. We have to form the complete stiffness matrix of a 3D beam element, which we will do now. Let us enter the same matrix again. Now, I am saying this is K matrix of ith member. Let us enter the labels T, R, B, L, N, P, H, S, W, and M, O, Q. Let us enter the values T, R, V, L, N, P, H, S, and W, M, O, and Q. Okay. Now, you know, by giving unit displacement along x, we will get this value which is known to us, which is AE by L. So, E AX by L, and T and H will be affected. So, minus E AX by L. Similarly, by giving along H, this will be minus E AX by L and plus E AX by L, remaining all are 0. I am not entering the 0 values. Okay. So, let us enter them. Okay. Next one is giving unit displacement along R along the y axis. We know, comparing the beam element, the stiffness matrix can be entered in simple as R P. So, R P, okay, S and Q will be invoked. Okay. R and S are reactions, P and Q are moments. Therefore, in simple terms, this will be 6 E I Z by L square, Q will be again minus 6 E I Z by L square. The reactions will be 12 E I Z by L Q and minus 12 E I Z by L Q. So, 0, 0, 2 zeros, 0, 0, 2 zeros. Let us do this for S also. In S, you know, 3 will be negative, only along S will be positive. So, this is positive, remaining all will be negative. Remaining all are zeros. Which is convention known to us. then let us give unit rotation about z axis. We already know this value. Okay. So, that is going to cause invoke PQRS. So, P, R, S and Q, only this will be there. We all know that is going to be 4 E I by L. So, 4 E I Z by L and Q is going to be 2 E Z by L, which we already know for a 2 dimensional beam member. I am entering them in green. Okay. The reactions are going to be along R is positive. So, 6 E S by L square, along S it will be negative 6 E Z by L square, remaining all will be 0. So, 0 and 0, 2 zeros, then 1 0 and another 0 below and 2 zeros. Okay. Similarly, we can do it for Q also. This is going to be 6 E A Z by L square, then at P this will be 2 E A Z by L, for Q is going to be 4 E Z by L, and for S is going to be negative minus 6 E Z by L square. So, reactions are L square, okay, and moments are L, remaining all are 0. So, 0, 0, 2 zeros, then member, zero, 3 zeros, then value. Okay. So, we have entered the 6 columns which are conventional for a simple beam element, which we already know. Okay. Let us know the remaining with red color, which is new for the 3 dimensional member. So, let us give unit displacement along V, and we will get. Now, let us try to understand how do we get I Z here, how do we get I Z here. Okay. So, look at the bending plane. When I give unit displacement, the rotation contribution comes about the z axis. Okay. So, K P comes about the z axis, that is why we are using I Z here. Okay. That is why you use I Z everywhere. Let us now go to the unit displacement along z axis, which is V. When I give unit displacement along z axis, which is V, okay, it is xz plane. So, now when I give displacement, the rotation is going to happen about y axis. So, I should use I y. Okay. So, be careful, we should use I y now. So, now this is going to be 0 0 12 E I y by L cube 0, again V means n. So, minus 3 6 E I y by L square, then zeros, then W will be invoked. So, minus 12 E I y by L cube, then minus 6 E I y by L square. So, V, then correspondingly is going to be W, is it not? V and correspondingly W. So, let us fill up this column now. So, W column, which will have the same values, but with a different sign convention. I by L cube 0 6 E I y by L square, then 3 zeros, then 12 E I y by L cube, then 1 0 6 E I y by L square and 0. Now, let us give unit rotation about x axis, okay. That is what you are going to do about x axis. You are rotating it about x axis, so you get torsional moment, okay. So, I should use now only, you can see here only L and M are invoked, only L and M are invoked. So, L will be again, so these 3 are zeros, this will be G I x by L, and till M all will be zeros, this is going to be minus G I x by L. Similarly, with M, L and M will be invoked. So, this will be 0 minus G I x by L, remaining all are zeros, and M it is going to be G I x by L positive, remaining all are 0. Let us now talk about the last column, which is rotation about N. Okay. So, when I give that, I am going to invoke moment about I y, okay, moment about I y. So, I should say, if we talk about N, the degrees of freedom are N, V, O and W. So, N, V, O and W. So, let us talk about N V. So, T R 0, V is present. So, it is going to be minus 6 I y by 12 by L square, okay. Then this is 0, 4 E I y by L, next is 0, these two are zeros, W will have 6 I y by L square and 0, and O will have 2 E I y by L. Let us the last column O, which will be again, these two are again zeros. So, this will be minus 6 E I y by L square. So, 0 going to be 2 E I y by L 0, then this is going to be 6 E I y by L square 0 and 4 E I y by L 0. So, friends, we have now all the coefficients of a 12 by 12 matrix which qualifies for the member stiffness of a beam element, which is arbitrarily oriented in space, which is going to make the space element. Now, let us see how to estimate this I x, okay, this I x. I x actually is called torsional constant. Now, for the beam element, with rectangular cross section, I x can be given by h t cube by 12 1 minus 0.63 t by h plus 0.052 t by h cube. This approximate, okay, where h is very large compared to t. So, I have a rectangular cross section, this is my h and this is my t. If h is very large compared to t, then I can use this approximate equation to compute the torsional constant. For rectangular cross section with very large value of h over t, I x can be approximated as simply h t cube by 12, where this ratio will go very low. In case of I sections, as shown, let us say this is T f, this is B f, breadth of the flange, this is T w, and this is H w. So, this is the web, this is the flange. Okay. I x can be, now the torsional constant is 1/3 of summation of h t cube, where h is the longer dimension of rectangle and t is the shorter dimension of rectangle. Having said this, now I can find the torsion constant for this I section as 1/3 of h is the longer one, let us say call this as member 1, member 2 and member 3. For member 1 it is going to be B f T f cube, okay. This is for member 1. Then for member 2, the longer one is h w T w cube member 2, plus again for member 3 it is B f T f cube, this for member 3. So, I can find the torsional constant approximately using this relationship. So, now for the 3 dimensional member aligned in space, we know how to compute the member stiffness matrix. For a beam element of space structure. So, we know that this k is going to be 12/12, which is actually an extended derivation of 2D system. We have also explained you how to compute the torsional constant using approximate relationship for these members. Friends, we will continue the discussion in the next lecture and try to see how we will transform these member stiffness matrices to global stiffness matrix with reference to the reference or global axis system. Then we will assemble this to form the K total of the entire space structure to analyze the structure. Thank you very much.